Hi everyone, in this video we'll look at motion graphs and see if we can analyze them a little bit further with some mathematical tools. So the first one, this position versus time graph, I'd like you to see if you can describe the motion of the object from that graph, and also if you could produce the velocity versus time graph from that position versus time. Okay, our description of the motion here, this is an object that while it starts in the negative All right. Hi everyone, in this video we're going to be looking at our motion graphs and see if we can analyze them a little bit further mathematically. So for the first one, I have a position versus time graph. Can you describe the motion of the object? So come up with that word description, and also could you produce the velocity versus time graph from that? All right, so our object starts with a negative position, and although it starts with a negative position, it still travels in the positive direction. Remember, up on a position versus time graph means you're moving in the positive direction. We also have positive slopes, but those slopes anywhere on this graph are all constant. So I would describe this as a constant speed moving in the positive direction. So for my velocity versus time graph, I'm going to have a positive velocity that remains constant. Okay? And I said we want to analyze this a little bit further mathematically. When I look at graphs, and hopefully as you get better at this, when you look at graphs, we're thinking about the different things that we can read or measure from the graph. And especially if it's a straight line, we think about measuring the slope. We think about the intercepts, both the x and y intercept, and what they physically mean, and also the area underneath the graph. And for those of you who are in calculus, that might make a bit of sense where we're headed, but we'll make some sense of it if you haven't seen that before. So, of course, the slope of a line graph, that is our rise over run. And the way that we can determine if it's meaningful or if it has physical significance is to look at the units. So in this particular position versus time graph, we have units of meters on the y-axis and time on the x-axis. So if I were to calculate the rise over the run, which would be change in position over change in time, the units of that measurement of slope would be meter per second. And meter per second we know we use for speed and velocity, so that has physical significance. And we said in the last video that the slope of a position versus time graph is the average velocity. So the slope in this case is meaningful. It has physical significance. The intercepts, I like to look at the y-intercept. And physically, what does it mean? So when time is 0, this was my position. So the y-intercept is just the initial position. Okay? And how about the x-intercept? When the position was 0, what time was it? So that would just be the time at which you're crossing some origin that was chosen for this particular problem. Okay? So the intercepts are physically meaningful. The slope is physically meaningful. Area sometimes will be physically meaningful. And when I say the area, I mean the area bound by our graph between the function and the x-axis. So in this case, it's this little triangle underneath of the time axis, and if I wanted to calculate the area, I would use the formula for the area of a triangle, and it would be 1/2 base times the height, where the base is our time measured in seconds, and the height would be our position measured in meters. If I were to do the area in this particular case, I would get a unit of meter times seconds, and that's not a physical quantity. It doesn't really have, it's not a useful value for us. It's not something that we've measured before, so meters times seconds has no physical meaning, so this one I'm going to rule out. But we can use this mathematical analysis on any of our graphs, and we're going to keep practicing because we'll be doing this a lot, and you can expect to have to do it on the AP exam. Okay. How about this graph? Do you feel confident that you could describe the motion of the object? Do you feel like you could produce the position versus time graph? So go ahead and try this first, and then we'll get to the rest of the slide. Okay, for this particular velocity versus time graph, it starts out with a big negative number and then it heads towards 0. So that is definitely slowing down, right? We're starting with a big negative velocity and we head towards 0. We're slowing down, but we're traveling in a negative direction. So our position versus time graph that would match this type of motion would be something that is starting out steep and negative and then heading towards more shallow or flatter. So something like this, where we're slowing down and traveling in a negative direction. So we started out really steep. We were able to travel a great negative displacement over a short period of time, but then we're flattening off because we were slowing down. Okay, and I want to do the same analysis here. I want to look at slope, intercept, and area and see if there's any physical significance to it. So the slope, if we did change in velocity over change in time, or rise over run, well, by definition, I know that change in velocity over time is acceleration. And also if I look at the units of the slope would be meter per second divided by seconds, or meter per second squared, which we said was the unit for acceleration. So slope checks out. It has physical significance. The slope of a velocity versus time graph is the average acceleration. How about the y-intercept? Well, when time is 0, what was the velocity? So that would just be our starting velocity. And how about the x-intercept? When the velocity was 0, what time was that? So this is just telling us any times where the velocity was 0. Okay? So that would have physical significance as well. And if I were to check the area on this one, again, the area bound between our graph and the x-axis, the units would be, let's see, meter per second for our height and seconds for our base, because again we have a triangle. So that would be a meter per second times seconds. And when you have seconds on top and seconds on bottom, they cancel, and you end up with the units of just meters. Well, what do we measure in meters? Distance and displacement. And it turns out that the area beneath or bound by the velocity versus time graph is the displacement. Okay? And that's similar to how we developed the kinematic equations. You're going to end up in a similar place. So we can get the displacement from the area bound by a velocity versus time graph. Okay? So we have those different velocity versus time graphs that we can see. We said we can see constant velocity, we can see speeding up, slowing down. We're probably not going to see a curved velocity versus time graph. And in terms of what we're doing right here, finding the area beneath it, once that graph is curved, it's a much more challenging formula for developing the area beneath, right? So we can do areas of rectangles, we can do areas of triangles. We're definitely equipped to do that. So if I have an object like this that's traveling at a constant velocity, I could find the displacement by determining the area bound by that velocity versus time graph. Now, this doesn't stop you from using the kinematic equations. You could still read your velocity at the beginning. You could read your velocity at the end. So you have your v initial, you have your v final. You could also read what time this event occurred. So it took 12 seconds. You could find the slope to get the acceleration, and in this case the slope is 0 because we're traveling at a constant velocity. And you could absolutely use your kinematic equations to do this. So you could list your v initial, v final, and time, and you could solve for the displacement that way. But this is just a graphical interpretation, so maybe a quicker way to understand what's going on, and that is if you see a velocity versus time graph, the slope is the acceleration, but the area bound by that graph is actually the displacement. Okay, so in this case we have a positive displacement of 216 meters, and this was just the area of a rectangle. When we see changing velocity, like this object that is speeding up in a positive direction, in all these values of velocity are positive, so we're traveling in a positive direction, and the values are getting further from 0, so we're speeding up. So in this case, we would have a triangle, and I could find the area of a triangle by doing 1/2 base times height, and I end up with a displacement of 64 meters. Again, you totally could have done this with the kinematic equations. You have a v initial of 0, you have a v final of 32, and you have a time of 4 seconds. So that's 3 kinematic variables. You would be able to use the kinematic equations to find acceleration and displacement. This is just our graphical understanding of what's happening. Okay? And it can get just a little bit more challenging if we have a non-zero initial velocity. So non-zero initial velocity is going to make this now a trapezoid. And I personally don't have the equation of a trapezoid memorized. So for me, I would simplify this by, when I see that trapezoid, it looks like a triangle sitting on top of a rectangle. Right? So I would calculate the area of this rectangle, calculate the area of that triangle, because I'm very comfortable with those two shapes, and then I could add them together. Again, if you wanted to, you could use kinematics. You could say V initial is 4, V final is 12, and time is 5 seconds, and you could find the displacement that way. So we have a positive displacement of 40 meters. So far, all we've seen are positive velocities, velocities that are above the time axis. We know that if the velocity is below the time axis, we're traveling in a negative direction. So this area that's bound by our velocity versus time graph means that it's a negative displacement. So if you're traveling in the negative direction, it should make sense that our change in position or our displacement is negative. So in this case, we have negative 64 meters for the displacement found by doing the area of that triangle. Okay? And this will allow us to do multi-stage motion. So you can see a graph with several different runs of the object, and if we wanted to find the total displacement, we're just going to add up all of the areas that are bound by the velocity versus time graph. And any area bound above the time axis is going to be a positive displacement. Any area bound below the time axis is a negative displacement. So in this particular case, this was an object that went forward for a certain distance, then went in the negative direction or backward for a certain distance. And since those two areas are equal, in this particular case, the object has gone back to its original position. So I could then produce the position versus time graph for this object. For the first 5 seconds, it was slowing down in a positive direction, so it's going to look something like this. And then for the last 5 seconds, it was speeding up in a negative direction, so I should be getting steeper and negative. And since I know it was 5 seconds in the positive direction, 5 seconds in the negative direction, I had started with plus 49, I had ended with negative 49. These two areas are identical, which means I've returned at the end back to my original position. So the total displacement in this case was 0. Okay, so that's just a little bit more analysis that we can do on the graphs. We can now provide a word description, a motion diagram. We can move from position versus time to velocity versus time. We can go from velocity versus time back up to position versus time. And we can use the area bound by the velocity versus time graph to determine the displacement. Okay, so that's enough for our mathematical analysis of the graphs. Thanks for watching.